Okay, so as I said, we're going to repeat the problem from the last video, which is finding the surface area of this portion of the paraboloid, z equals x squared plus y squared, which is just r squared, if I write that in cylindrical coordinates, below the plane z equals 5. Okay. Last time we did this by using the parametrization that essentially just let x be u and y be v, so we were taking advantage of the fact that z was a function of x and y. Now I'm going to take advantage of the fact that z is a function of r and theta, and so I'm going to say x is r cosine theta, y is r sine theta, and z is r squared. So my parameters are r and theta. Now I know I'm trying to essentially describe this disk of radius root 5, but now I'm doing that in the r theta plane, where my parameters r and theta are rectangular coordinates. R is varying from 0 to root 5, theta is varying from 0 to 2 pi, and so we're integrating over this rectangle, which I will call D. Okay. Now, once I apply this function to this, that's going to map the x and y parts to a disk, and then of course attach the height z, so that we're going to get this portion of the paraboloid. So r and theta will take on their role as cylindrical coordinates once we're in 3 space. But in the parameter plane, they're just rectangular coordinates. Okay, so I can calculate the partial of r with respect to r, and that's going to give me cosine theta, sine theta, 2r. And I can calculate the partial of r with respect to theta, and that's going to give me negative r sine theta, r cosine theta, 0. Okay, no thetas there. So then I can calculate my cross product, del r, crossed with del r del theta. That's going to be a symbolic determinant, I, j, k, cosine theta, sine theta, 2r, negative r sine theta, r cosine theta, 0. So for the i's, I'm going to get nothing minus 2r cosine theta. For the j's, I'm going to get negative 2r squared. Yes, negative 2r squared sine theta. So let me check. That should have been 2r squared cosine theta. I'm sorry, there was an r there and an r there. So this first component should be 2r squared cosine theta. Negative 2r squared sine theta. And then here, I'm getting r cosine squared minus a negative r sine squared. And that's going to be just an r squared. Now I'm running short on space, so let me write out the longer version. That was r, I'm sorry, that's just an r. Yes, that was r times cosine squared theta minus a negative r times sine squared theta, which is plus. So that was r times cosine squared theta plus sine squared theta. And of course, that's just 1. So that's how I get that that third component is just r. All right. Okay, so now I need to calculate the magnitude of that. So the magnitude of del r crossed with del r del theta is going to be the square root of this squared, which is going to become 4r to the 4th cosine squared theta, plus this squared, which is going to be 4r to the 4th sine squared theta, plus this squared, which is just r squared. Now, these two terms, that's 4r to the 4th times cosine squared theta plus sine squared theta. And of course, that's just 1. So this becomes 4r to the 4th plus r squared. So I can factor out an r squared. And then it's times 4r squared plus 1. So that's the square root of r squared times the square root of 4r squared plus 1. That's the absolute value of r times root 4r squared plus 1. But r was varying just from 0 to root 5. So that's bigger than or equal to 0. And so this becomes just r root 4r squared plus 1. So at this point, I can say, okay, we're getting the double integral over d of r times root 4r squared plus 1 dA. But here, I'm already working in the r theta plane. So I am not switching to r and theta. I'm already working with them. They're my rectangular coordinates. This dA is just dr d theta, because I am not switching to polar coordinates. My function that parametrized this surface changed r and theta from just being rectangular coordinates in the parameter plane to taking on their role as cylindrical coordinates once they were in 3 space. But that transition and how that morphs this area into the area of the paraboloid, all of that is taken into account in this formula because I've been working with r and theta from the beginning. I am not switching to them. So this just becomes the integral from 0 to 2 pi, the integral from 0 to root 5 of r root 4r squared plus 1 dr d theta. And if you look back to the last video, what we had done is we had set things up originally in terms of parameters u and v, and then we'd switched to polar, and we got exactly this integral. So real quickly, what we did was just a quick w sub. We let w equal 4r squared plus 1, so that dw was 8r dr. We introduced an 8 and a 1/8. And so then we got 1/8 integral 0 to 2 pi, integral from 1 to 21, because our limits of integrations changed, w to the 1/2 dw d theta, and that was 1/8 integral 0 to 2 pi, 2/3 w to the 3/2 evaluated between 21 and 1, and then d theta. That was 1/8 times 2/3 integral from 0 to 2 pi, 21 to the 3/2 minus 1, d theta. And that gave us 1/12 of 21 to the 2/3 minus 1 times 2 pi. And then we just canceled a factor of 2, and this was our final answer. I went through that last bit really quickly because we had just done it. It was exactly the same problem. Okay, but the difference is, in one case we started with parameters u and v, and then when we switched to r and theta, we were switching to polar coordinates. Here, we started with r and theta as our parameters, so the function r of r theta, that gave me x, y, and z in terms of r and theta, incorporated the transition, the morphing that takes place when we allow r and theta to take on their role as cylindrical coordinates.